Hi, I am planning to do an exclusive video series on Linux kernel device trees. Of course, I have covered various aspects of kernel programming as well as kernel module programming and Linux kernel device drivers and stuff like that. But this time I am thinking I can start a fresh series on device trees. There's quite a lot to discuss. I do time to time discuss in my sessions with my students, but I thought I can take a video series as well, but based on the viewers' popular demand. So give this video a thumbs up and let me know in the comments as well if you are looking forward for such a series. Like I do all my video episodes, the way I am going to cover is the way I approach architecturally. Being myself an systems architect, I want to give certain views besides giving extensive demos and stuff like that. So if you are looking forward for this video, give this video a thumbs up. Once it reaches a specific threshold, I am going to start this fresh video series. So let's get to the show. Hi, welcome to the next channel. So in my last episode, I mentioned in the description and as well as I pinned a comment mentioning that I'm going to discuss about when to use a thread and when to use a multi-processing. I mean when to use multi-threading and when to use multi-processing. See, this thing, it is not new. I have kind of vaguely discussed in many episodes. I have even done some R&D kind of stuff with multiple threads versus multi-processing and stuff, but it's nowhere specifically discussed about when exactly you can do this type of load sharing. See, the whole point of doing multi-threading or multi-processing is you share the existing load so that you can do like a divide and conquer type of way, or you can also run if you think about my case, I run various services in my network stack. So in that case, what happens is I put different services at different threads, and sometimes multiple modules, I split them into multiple processes so that it is not all dumped in one process and I got around 10 threads or something in that process. So instead what I do is some processes will have multiple threads, and if it is completely different role it is doing, I can split into different processes as well. So which is why in this last video I mentioned that I am going to shoot a video about that the process address space, because when you discuss about multi-threading and multi-processing, everyone in the internet discusses about threads share the common address space versus processes are going to exist in different address space. So this is quite obvious. So this is anyway you will get everywhere in the internet. So I'm going to discuss something beyond that as an architect's perspective, like I do always. See, multi-threading versus multi-processing, you can search more or less you will find things like this. See, we can open multiple sites, and they kind of give the fundamental differences. See, this is happens in the system part, right? See, you can see there is a huge chart, so you can open any of such websites, and what happens is you can go through that. See, this is being discussed in a student's perspective. So if you are still beginning, if you are new or something like that, this is enough if you are a student or something, so that you read this, and perhaps in your syllabus, academics, they are asking these kind of questions in your exams, it's fine. I'm saying, if you are doing real hardcore coding, then you need to know when I can split my code in, when I can organize my code in multiple threads versus in different processes. So I'm kind of giving a perspective like that, so that if you engineer, if you write any software, how you can take such a decision. So it is very important. It's something, it is already there, then why I should take the video? The reason I'm taking the video is so that if you architect something, you can understand the intricacies, not just in the definitions perspective. It's all about, it's a personal choice, and also it's all about how your architecture of your software code it demands. Okay, so you can see that the obvious difference is both multiprocessing, as the name says, it's different processes. So if you see, for instance, you have this Firefox, and I have some 4-5 tabs, right? So different tabs and different services. Firefox will always spawn multiple processes, which you can check over here. See, ps-aef, and we filter Firefox, and we just do grep Firefox. Yep, you can see there is one main parent process 2368, and then this is spawned all this different processes. So these are not threads, because a thread is the same process address space, which means it is going to be existing as single process. So if in a process, you can split into multiple threads using pthreads or some library like that. So this way, if you see, these are different independent processes, and we don't know, each process may contain multiple threads as well. So which is what is this whole video about. So what happens is, which is why they are saying, when you think about a process and threads is going to be the same address space, which means different threads when you spawn within a process. Let's take some Paint application, and let's just write processes. This is multi, and you have the threads. These are, of course, threads itself is plural, so we can think this is within a process. Okay, so that's what architecturally it is. So you have this this thing, you can see, increase computational power. So this is the basic idea behind this. Helps you to create computational threads of a single process, increase the computational power, which is why I'm saying it is all about load sharing. Okay, then it allows to multiple process concurrently, and the same thing again, not much of a difference. In the memory part, you can see there different allocates a separate memory and resources for each process or program, which is why I'm saying what they meant is, it is going to be existing in a different process address space. It is good to use this term as address space, which many fail to understand. So which is why extensively I took a detailed video about process address space. I'm going to link this video in this description. And as well, there is this kernel address space as well, which I discussed in this kernel module. What is a kernel module? See, this thing you will find in various pictures like this, process address space, and you will find architectural pictures like this. See, you can see there you have this process address space, and kernel maintains this instance per each process, of course. Okay, and this is going to tie that PID, of course. You need to know what is the process ID and stuff like that. So which is why each process is going to have in its own address space. So what happens is, when you split into multiple processes, the idea is each instance which is doing this concurrent processing is going to have its own address space. So if some process gets some segmentation fault or something, because obviously we know if there is any memory leak or something, the segmentation fault happens in the process level, versus kernel is going to have that kernel loops and stuff. So kernel is completely different. In the process, if there is any segmentation fault happens, that process will get killed, it will be terminated by the kernel. So something like that happens, you can still run the other processes without any hitch. So that's the main advantage of using many processes, okay, in architectural perspective. Hence the one word, when you discuss about this address space, it has lot of implications. Hence if you think about this thing, you have this kind of an arrangement. So what happens is, if you take in process, multi-process, of course, you have separate independent address space. So that is something which is obvious. Space. So that is something which is obvious. The other thing is, you should understand, you can run some processes in one server if you are using it for some huge mainframe computing, or some kind of supercomputing, cluster computing, or something with many Xeons, and you want to offload and you want to share this load to all together in different servers. So in that way you can run it in multi servers and stuff. Okay, of course it is going to be multi systems, right? So it can run in multiple systems. See, something like this is not of course possible with threads, because it is going to be sharing the same address space. So that is something which is obvious. See, as you do this way, what happens is, if different processes wants to communicate, then you need to have a different IPC mechanism. You need to have some IPC mechanism. So that is quite obvious, and it is, if you need to share some data between different processes, some common data, and then in case if this shared data is going to be accessed simultaneously, reads and writes and stuff like that, then you need to use some type of synchronization within this processes. Okay, and hence this is where it gets cumbersome, and it depends how you solve the challenges. As you do this load sharing, the challenge is, the more synchronization you use, it defeats the purpose, because something have to end and then something have to start, and this defeats the purpose. Again, I have discussed quite extensively about process synchronization disadvantages and stuff like that. Generally, if you ask me, I am not a big fan of synchronization aspect itself, because if you have a common shared resource, something like a buffer or something, as you share it within multiple threads or multiple processes, then you need to synchronize, and you will come up with a different kind of problem. So sometimes it is okay to have independent buffers if the architecture demands. Okay, I am not saying it is always possible. Sometimes you need to have synchronization as the only last resort, but you can try something like that. So typically that is one obvious bottleneck. So you need to have some type of IPC. So IPC Linux we type, and we can get excellent resources like this. So you need to have some type of IPC in terms of getting access between multiple processes. So you need to have some type of IPC. Okay, the whole idea of IPC is to share the data between different processes, because each are in a different address space. See, imagine different you have different address spaces for each process, then you need to have some type of IPC to bridge if you need. Okay, if you need, so conditions apply. So if you don't need, then you don't need any IPC. But if there is any common data, some config or something like that, something like this you want to share between multiple processes, then you need to have some type of IPC. So it can be some config, it can be some runtime information, something like that. So if you imagine this Firefox processes, imagine Firefox browser settings or some running context of Firefox. If it has to be shared between multiple processes, then they need to have different IPC communication. to share in between them. So same is the bottleneck. Again, you have a common resource, so you need to have some type of synchronization over here, some sort of a synchronization. You need to lock and then you read or write and then release the lock. Other guy or the other process will lock, read, write, do something, and then he will release the lock. So this is a kind of bottleneck by itself. So this is the same going to happen even in threads as well. Again, if you use a common shared resource like some type of a global variable or something like that, okay, again, but you don't need any IPC because they are all sharing the same address space. So that's the main advantage of using different threads architecturally. So still may need some locks. So what I meant by lock is synchronization, but you don't need any IPC. So that's the whole point, okay, you don't need any IPC. So different threads you may have within the same process, and there is some sort of a shared resource like this, then different threads can communicate between that, because all it is going to be existing in the same address space. So everything is in the same address space, so you don't need any IPC here, okay. So but you need some type of synchronization. So as you communicate and as you use that, you need still some sort of a synchronization over here in multi-threading. So all these threads is going to exist in the same process address space. So you can imagine this green color rectangle is your address space. So everything is in the same address space, versus these red boxes are itself are different process address space of that respective processes. So this is the sort of a bottleneck. So where exactly you can use threads in software development is you can use it for some sort of a file processing engines, or in my case I use like this extensively in my network stack. That includes even Toffee. I use extensively, like I said, I do use multiprocessing to split module wise separation or the role at which it processes the packets, and then I do this multi-threading to split in terms of egress and egress type of similar module like processing. Suppose if some module is doing compression or something like that, what I do is it will handle one side compression of the packets, it will handle decompression of the packets on the other side. So egress, it is going to compress and send it out to the WAN networks, and ingress ingress, which is coming from WAN to local area network, I am going to decompress this packet. So something like that. I am saying I am not just doing this alone, I am doing several things, but I am giving an example. So in that case, I split the LAN flow, LAN to WAN flow and WAN to LAN flow in different threads. So it is going to be single module, and it is doing this kind of a task in this fashion. I can also split in a different way. I can for example, I can even split in different way. I can split different processes to handle LAN to WAN and do multiple iterations of packet processing. So what I meant iterations is it does several type of packet processing. Okay, it's just not, like I said, it's just not compression alone. So it can do multiple steps of packet processing of one direction in one process. The other direction I can do it in other independent process and do multiple iterations of packet processing. So I can have any type of option in that way. So in this case, if I split in threads, what I am doing is I am doing direction of the packets I am handling in each thread, and each process is going to have a different role. So this is the architecture part of my project. I am giving an sample. Hence I am saying sometimes you can combine in one project. Let me summarize. See, sometimes you can combine one project can contain both of these. Okay, hence it is not something that you go with one sort of a direction and this is having an advantage, this is not having a disadvantage. It's not like that. As an architect, I am saying you just need to take a call. You need to see what it exactly suits you, and you need to take pen and paper, write down the pros and cons. If you use this way, how you can solve a particular challenge and how you design your product architecture. So it takes a lot of time. I have done earlier, I have done only with threads. I have not used different processes. Then I started, once the code is mature, I started splitting into independent processes itself. Hence sometimes I may need some lightweight IPC, but other than that it just works fine. And there are also some pipelines which I push packets. Those are heavy bandwidth IPC which I use. So again, I need to be critical which IPC mechanisms I need to choose. Hence I am saying this video is going to serve as an add-on. The more obvious things which you anyway read over here in terms of process and multi-process and multi-threading stuff, you can see anywhere in the internet, I'm saying. But on the other side, when you think like an architect, you have different challenges about the address space. See, in this case, in different threads are there. If one thread crashes, what happens actually? If one thread crashes, some segmentation fault or something, it is going to bring down the entire process, and whole number of threads you signed up or you registered is going to get killed okay, in that process. But in this case, if you split into multiple processes, if one process is getting some segmentation fault and it crashed, still the other processes will run. So in this way, you need to do a lot of a lot of factors you need to keep in mind, and this is something I do extensively discuss. And when I discuss with my student, we do have extensive sessions. We may have around 2 times on this itself, which is close to around 4 to 5 hours of discussions. I am kind of sort of compressing, but the more you explore, it becomes quite evident, and it's a huge interesting aspect by itself. Hence I am saying I am just trying to compress everything into one package so that it is not too lengthy in single video. And moreover, there are several aspects to that when I discuss how you compute it, how you check how many instances you want. For instance, okay, multi-processing and multi-threading, how many threads you want, how many processes you want, how you judge that, how you architect this thing. Do you need 100 processes, or you need 50 processes with 2 threads, which is going to be 100 compute instances, or you want 25 each into 4. Okay, so 25 threads of each process of 4 instances. So 4 processes with 25 threads is going to be 100 compute instances. So there's a lot of things are involved. I'm saying this video, you take it as a small add-on. You have the obvious things which you read in the internet, but I'm saying in this way, you need to think that it is just not about that. You need to take care of various aspects. When it comes to processing, multiprocessing, you have one obvious advantage, but the disadvantage is you need to use some IPC, versus here there is no IPC required. So there is no such bottleneck of data going from one thread to other thread and all, because it's all in the same address space. It is all the same process actually. Okay, you don't need any IPC. But if you use a common shared resource, then still you need some locks within the process context. See, these locks are not spread across multiple process context. Hence, it is going to be quite lightweight and quite easy to manage these locks, versus you put locks over here, because these are spread across multiple processes. So hope you got some context and big picture. We do generally discuss a lot, and this is quite a hot topic, especially some of my senior students, because they do work on huge projects, and sometimes they may hit upon some performance bottlenecks, and sometimes even I do get some independent client sessions. Not students, it may be a client, they may be having some issue in their production software, and they may discuss these things, and they book for a session, and then they discuss about these things. So it is a huge subject by itself, but I tried giving some vague idea so that you get that kind of big picture. Okay, so if you have anything to discuss, be in touch via mail or post your queries in YouTube comments. Thanks a lot for joining me. Stay tuned. Have a nice day. Bye bye.